Hey everybody, I just wanted to make a quick no-frills video about the closure of operations on regular languages. So if you remember, closure just means that if we apply one of these operations like union or concatenation to two regular languages, we expect a regular language to come out. So in a previous video, we talked about union and we showed how to do that with DFAs, and it was kind of convoluted. Now that we have nondeterminism in our tool belt, it is much easier to prove each one of these operations. So let's just start with union. We did this one previously. So let's add another start state here. We'll call this state 0. That is massive font. That's tiny font, but whatever. At start state. And then we will take the start states of our existing DFA and we will add them to this new start state with an epsilon transition for each one. So I love how that's not taking. All right, there we go. So now when we start up our machine and feed it an input, it will non-deterministically pick both of these paths and travel down each one. And if one of these machines, either or, accepts this input string, then the machine terminates in an accept state and hooray, everything's good. So just like that, we have proved the union of two regular languages. We just add a new start state with an epsilon transition to each start state. Now, in order to prove concatenation, we have to do something a little bit different. So if we take our machines, and remember that concatenation is when we take an acceptable input from language 2 and we tack it on to an acceptable input of language number 1. So what we are going to do is take the end state of our first machine and add an epsilon transition to the start state of our second machine. So just like this. So now when we end up in this accept state, we're going to non-deterministically choose to follow this path here and see if the rest of the input string works with our second machine. So if this is accepted, then hooray, we have proved that the new string is a member of this concatenation language. So that one is very simple to prove as well. Just take the accept state from machine 1, add an epsilon transition to the start state of the second machine. The last one that I want to talk about is Kleene star. So if you remember, Kleene star is when we take the acceptable inputs from language 1 and we just keep adding them together, possibly forever. Kleene star also includes the empty set. And you can see I've kind of gotten ahead of myself here and already drawn this, but this was the machine that we were working with in our last video. So here, in order to prove this Kleene star operation, what we can do is we create a new start state for our machine. We'll call this one 0 again, like we did previously, and I don't know why typing is not working, but we add an epsilon transition from this new start state to our old start state. This allows us to accept the empty state as an acceptable string. The second part of this is every time we have an accept state, we are going to automatically transition back to our start state using an epsilon. And so kind of like concatenation, we want to check if the latter half of a string after something that has been accepted, we want to check if that is a member of our language as well. So in this case, say we've got something like, dog, good, and apple is our language. Once we complete a run through this machine on something like dog and we end up here and the second half of the word is good, we are just going to shift back to this start state, come through here and work through our machine again. So with that, we have talked through how to prove this closure using nondeterminism. Quick video. In the next one, we will talk about regular expressions and how they relate to these automata and regular languages. See you there.